Okay, so this is the last lesson. We're just going to finish up this, puts everything we've learned in this unit all together to graph polynomial functions. So we took a little sidestep and did rational functions for a day and a half or so. And what was the main additional feature we had to focus on to help us graph those types of functions? We had to worry about the asymptotes. So the nice thing about polynomial functions, they're asymptote free. So you just have to worry about horizontal tangents or when derivative is 0. You don't have to worry about the undefined options. Okay, so we got through we were looking at the example 1, which was a cubic function. And the first 3 parts of our analysis had nothing to do with calculus. They were all just looking at features of original function f of x. So we figured out intercepts and we figured out the symmetry. Okay. Then we were finding the critical points. So the critical points are the locations where the derivative is 0 or undefined, but in case of polynomial, we only have to check where the derivative is 0. So we did that. We found those 2 values. We found the corresponding points, and then used those as our boundaries for increasing, decreasing intervals to confirm when the function's increasing or decreasing, and then confirm where we have local minima and maxima. Yeah.
Is there a more functions in here?
That's the next lesson, tomorrow, Friday. Yeah, there is. It's one type, but once you get the hang of it, you'll notice, it's once you learn how it works, it's like wash, rinse, repeat. It's like do the same thing every time. So you'll see tomorrow. So, and then what did we do next? We had to we went one level deeper and did the second derivative because that will tell us concavity. So we found where the second derivative was 0, and we found the concave up and down intervals, and use those to put it all together to make our sketch of the cubic. Okay? Okay, so now we're going to move on to a second example. So what we're going to do first is just kind of say, here's the summary of all the things that we just did, just to kind of get an idea of if I have to sketch a polynomial function, what should I look for? So find the intercepts. Now, I put a little note there. It says only find x-intercepts if it's not time-consuming. So, in the case we just did, it wasn't it wasn't too horrible to find the x-intercepts because it was nice and factorable, right? Even if this wasn't factorable, the x squared plus 6x plus 9, say it was some other quadratic. Even if it's quadratic and it's not factorable, it could still be solvable. I consider that still not time consuming because you're using a formula, you can just plug into your quadratic formula. So the idea here is, what if it's not quadratic? What if you have a cubic or a quartic that you have to try and see if it's factorable, but maybe it's not, that kind of thing, right? And so if you're about to try and find the x-intercepts and it's going to take you almost 20 minutes or analysis of trying to figure out even if you can, then you kind of just say, okay, I know there are probably x-intercepts, but I'm not going to spend the time to look for them. I'm going to find all the features I can from the other piece of information, the derivative and the second derivative. Does that make sense? So we'll see that as we proceed. It potentially shows up for some questions. And sometimes your teacher might be nice and say, hint, the x-intercepts are at negative 0.215 and 7.137. So you're like, okay, there they are. I'm just telling you where they are because you can't find them on your own. Fair enough? Okay. So everything else in the list has to do with derivatives, right? So you're finding the first derivative to identify critical points, and then determine intervals of increase and decrease, and then you can classify your critical points, local or absolute if possible, for the min-max. Okay? And then find the locations where the second derivative is 0, and then identify intervals of concavity and points of inflection. So that's the set of steps. Because if you have to kind of create your own set of steps if you're presented with a question like this. Okay, this is kind of like how the assignment is set up, right? Analyze the key features of this function and then make a sketch of it. But it's kind of like, it's not like part A do this, part B do this, part C do that. You kind of have to just do DIY, do it yourself, figure out all the pieces to make your sketch. So let's go for it. So let's start with looking for intercepts. In this case, are we feeling that the x-intercepts are going to be time-consuming to find? Okay, so I'm gonna do, so x-intercepts, I'm going to say too time consuming to find. I'm literally going to write that.
We would write that on that.
Yeah, as long as it's not factorable. As long as it's not factorable. Yeah, well, like you look, you at least took a moment to check, right? Okay, is it going to be possible? Like, do you guys get if it was x to the 4 minus x squared or something? Oh, I can factor out x squared, factor out. I can maybe get some zeros, right? So if it's a simpler expression, it might be possible to find, right? Your zeros. I'm looking here. It's 5 terms, the quartic. The only way you're even going to attempt to do this is factor theorem, right? I'll tell you right now, the test will be a factor theorem free zone. Okay? So what does that mean? You guys get this still might have zeros, but it's going to be too time consuming to find them. So just recognize that there will be some. So when you draw your graph, don't be surprised that you cross the x-axis. We just don't have the specific locations. Okay. How about y-intercept? Well, that one's always easy. Y-intercept. Y-intercept, you just put in 0 into there, and you would get negative 18. And so I now have 1 anchor point. Okay. So this is where like a highlighter is useful. Like as you proceed, if you find any points that you know are going to help you make your sketch, kind of just identify them as you go. Okay. So right now I could plot that point, but I'm not going to plot anything yet because I don't know the big picture of what numbers I need to fit on my scale. So we don't touch the graph until we've got all the info found. So, question.
Will a scale ever be given on like the graph, or do we have to make that ourselves all the time? Like a little like.
For these ones, you're gonna have to make it all the time. Because that's part of it's kind of like it's part of the process of you making your plan of how you want to graph it.
Okay.
Okay, so all I'm going to give you are the axes. Now, the other thing you can look at that has nothing to do with calculus is the symmetry. Now, in this case, we can, you know, if I said look for symmetry, just to practice, I'm gonna still look for it. So for symmetry here, do you guys remember the symmetry test? It's everywhere there's an x, we put in negative x. So f at negative x is going to be negative x to the 4 minus 5 times negative x cubed plus negative x all squared plus 21 times negative x minus 18. Do you guys get, we're going to get the flipping back and forth from positive, like same sign, change sign, same sign, change sign. Because every term, degree 4, 3, 2, 1, 0, there's a term of every degree here. When you raise a negative number to a positive, to an even exponent, what happens? Negative base to a even exponent, result is positive. Negative base to an odd exponent is negative. So I'm going to end up with same, x to the 4. This is the one everyone gets tripped up on. So negative x all cubed is negative x cubed times negative 5, positive 5x cubed. Negative x squared is x squared plus x squared, minus 21x minus 18. Same, opposite, same, opposite, same. Right? That's what we've got here. So in that case, it's neither the original or the exact opposite of original. That's what the last statement's saying. The f at negative x does not equal original or the negative of the original. It's not the same, it's not the exact opposite. So therefore, f at x has no symmetry. So if you're putting that in a table, you can just write none or write no symmetry, okay? If it's even symmetry or odd symmetry, one of those two would be true. Either it would equal f at x or would equal negative f at x. Okay, so everything I've just done here, I could have done in advanced functions because this was just information about f at x. So there's my info I'm looking for that's directly related to f at x. So now let's start looking at what the derivative will tell me. So what do we want to look for first? First derivative, and the first derivative corresponds, looking for a first derivative, that's going to help me find what first? Like what's the key feature I'm looking for? The increasing, decreasing intervals, which will correspond, the first thing I'm going to look for is the critical points. Do you want to put that as a big umbrella of increasing, decreasing? Sure, okay. increasing, decreasing. So I'm going to try and squeeze the increasing, decreasing stuff here. Okay. So what do I first need to figure out increasing, decreasing intervals?
First derivative.
First derivative. Okay. F prime at x is derivative of x to the 4x cubed. Derivative of negative 5x cubed, negative x squared. Plus derivative of x squared. And derivative of 21. Okay. Okay. So the idea here is, what's going to happen here is something that I just promised you won't happen on the exam. Okay. But you have a cubic, and it's not groupable. Is everyone cool with me saying that? So it's a cubic, it's not groupable. So the only way I could go about this is to do factor theorem. Oh. Okay, good old synthetic division, all that stuff. So since it might show up in the homework, let's do it once. But I'm telling you right now that on a test, on your assignment, hint, hint, on the assignment, this should be factorable, so you don't have to do this. Okay? But it is something you did learn in the last course. It shouldn't have left your brain completely. Okay? So if I let f prime at x be 0, I now have 0 equals this thing. Can't factor anything out. Okay. So what I'm about to do is the process of factoring this. So do you guys think the process of factoring this is almost like an aside? It's like go to the side here. Okay, and I'm literally gonna do an aside. And I'm gonna pick a different function name. I'm gonna say g at x be 4x cubed minus 15x squared plus 2x plus 21. Okay. So, okay, the only way this can work, I'm hoping and praying that it does, is that there has to be a number that would work with factor theorem for you to be able to do this question. Okay? So we're going to use, do you remember you have to look for possible values that we can possibly check with factor theorem. Do you guys remember how we check for those possible values, the only ones that could possibly work? If you think about it, you have to focus in on this constant, 21. It's all the divisors of 21, right? Any number that divides into 21, you're going to check, okay? But also, do you guys get, the answer could be fractional. Do you know what I mean? If there's a number, if you guys get there's a number in front of x cubed, you have to check, for instance, 21 over 2, 21 over 4, those might be the solutions as well. You guys following what I'm remembering? Is this ringing a bell at all? Crickets.
I'm kind of scared.
You're kind of scared.
Can we just plug in numbers
So don't just pick any numbers though. Like if you guys get 2, it's not even going to be possible. It's only numbers that divide into 21. Okay? Does one work? Like if you put 1 in for x, 4 minus 15, negative 11 plus 2, negative 9 plus 21, no. Does negative 1 work? Negative 4 minus 15 is negative 19. Negative 19 minus 2, negative 21. Negative 21 plus 21 is 0.
Thank you.
G at negative 1 equals 0. Therefore, by factor theorem, I was annoying. I made my students write that. Okay. Therefore, by factor theorem, something is a factor. So what's the corresponding factor? If negative 1 worked, then if I plug negative 1 in, I get 0. X plus 1 is a factor. Okay. So if x plus 1 is a factor, can I use that to find the other factor? And this is where.
Oh, he likes
No,
this
it's coming.
Oh no. Okay. No math knowledge. Okay. Okay. Somewhere in your brain. So you guys ever have synthetic division? You can, or if you prefer.
Cancel, put her away. Put her back in the closet.
I love that people watching back the video are just gonna hear cancel.
Okay. So who remembers how to set up this is the synthetic division setup? So what's the number out here?
-1.
Okay, and then across the top you put the coefficients. Okay. Now I think only one person that I taught last semester knows what I say now. Okay, what do you do with the first number? Bring it down or drop it like it's hot? Drop it. Okay. And then who remembers the repeated calculations? What do we do with -1 and 4? We multiply them and whoops, put that one on. Multiply them and then do what? Add. Multiply, add, multiply, add. That's the repeated process. You multiply, add. So -4, -15 plus -4 is -19. -1 times -19. Positive 19, 2 plus 19, -1 times 21, add 0. That 0 makes us very happy. Okay?
Now, what if we didn't get a 0 though?
It means that this part was wrong. This wouldn't have been true if this is true. Okay. So, all of that is side work. You can now go into factoring mode again. So we're over here. I've done all that work. It turns out I can factor 4x cubed minus 15x squared plus 2x plus 21 to x plus 1 times, what's the other factor, guys? Minus 19x plus 21. And then, I don't know if that's factorable too, but you guys get at this point, it doesn't really matter if that's factorable. It's a quadratic, so even if it's not factorable, it will be solvable, because you could use quadratic formula. So, you guys all know the fast check way to see if it's factorable or not is to just do quadratic, do the discriminant check. You guys remember discriminant? If you go b squared minus 4ac, and if you get a perfect square, it means it's factorable, because then the square root would work. Does that make sense? So if I do b squared minus 4ac, this is me just checking to see if this is factorable or not. So I don't got time for checking that. So b squared 19 squared minus 4 times 21 is 25. That is square rootable. So this is factorable. Okay? So now I'll actually spend the time to figure it out. So if it is factorable, so again, this is where you do an aside where you do decomposition. I think hopefully you guys recognize I've been very factor friendly so far, in the sense that I think every time you've had to factor, it's been a simple trinomial, right? I cut you some slack on this. But here, if I want to find the two numbers that's I don't know, you guys are decomposers, or do you guys what's your feel? What do you like doing here? Decomposition, guess and check. Decomposition. If you do a decomposition, right, what would be the two numbers that sum to -19 multiplied to 84? At this point, I almost want to do quadratic formula just because the numbers are big. And that's not a bad, you guys know how to do quadratic formula. It's going to work out nice. The quadratic formula will work out nice.
Are we going to actually do that next?
Well,
Or will you be factor friendly?
It'll be factor friendly, or I could still give you a complex trinomial that's a little more factor friendly than this one. Okay, but -7 and -12. So this is just me doing a quick work here. So 4x squared minus 7x minus 12x plus 21. Does everyone get?
Do it the other way.
It doesn't matter.
Guys, it's so much easier. Yeah, then you can factor then 4
Okay,
and
guys.
12 and 7.
Oh my gosh. Okay, so what can you take out of the first pair? And you're left with 4x minus 7. What can you take out of the second pair? 3, leaving you with 4x minus 7. It doesn't matter. Okay, it doesn't matter either way, okay? If you put the 12, you take out a 4. Ooh, okay, so then you have 4x, and then you have x minus 3. I don't care. Do you guys get that's all you really need to do now? I don't need to see this. This is like on your scrap paper, because I now know the two factors are 4x minus 7 and x minus 3. Yeah? No? Lost you? Brown has got me. You're good. Does everyone see? So that's me quickly doing decomp to find the factors. You could use quadratic formula to find the numbers that would create the factors. There's different ways you could do it. So, moral of story, I get 3 numbers, and the 3 numbers are, and if you want to really impress me, put them in numerical order. And the numerical order would be? Oh, okay. Boo. Okay, what are the 3 numbers? -1, 7/4 is smaller, 7/4, and 3.
Will you take off marks if they're not in order?
No, but you guys get, it's nice with them in order, because what are you about to do? You're about to make a chart, and you want them in order anyway. Okay, so obviously I need a lot more room than I let happen for that. So now we're going to do our increasing decreasing chart. And if our increasing decreasing chart, I feel like I'm going to go slow. So
See, now this time we have a lot of space before the ground.
you have no space here?
No, we have space and now you don't.
Okay, well, haha, now I do. Okay. So I'm just going to move my increasing, decreasing part is continued down here. Okay, so here's my chart. Okay, so x, f prime at x, f at x. So my 3 boundaries divide up the domain of x, which is -infinity to infinity, into 4 intervals. So the first interval is going to be from -infinity to, wow, it's so useful to have those in numerical order. Okay, and then we've got -1 to 7/4, which is like 1.75, right? And then 7/4 to 3, and then 3 to infinity. Okay. So what's happening when I let x be a number that's less than -1? I put that test, so pick a test value, -2, sure. So -2 plus 1 is what sign? Negative. 4 times -2, -8 minus 7. -8, well, so far positive, but that piece would be negative, right? -2 minus 3, negative. So I have a negative number times a negative number times a negative number is a negative number. We're looking at the first derivative, so a negative value of the derivative tells me what about original? Decreases. -1 to 7/4. Best example to choose there is 0. Again, you can plug into the factor form, but 0 is nice to just plug into the original derivative, because you go 0, 0, 0, and you're just left with positive 21. So positive increasing. 7/4 to 3, so we could pick 2. 2 plus 1 is positive. 4 times 2 is 8. 8 minus 7 is a positive number. 2 minus 3 is a negative number. And then 3 to infinity, so pick a number that's bigger than 3, like 5. 5 plus 1 is positive. 4 times 5 minus 7 is positive. 5 minus 3 is positive. There it is.
Miss, are questions on the test going to be this rude?
No.
Okay, that's good.
That's why you had an assignment. So you can take your time and go through this process on the assignment. Now, could I ask one piece of this puzzle for this function? Yeah. Okay, so that's what you're going to start noticing. It's like, here's a function, tell me the intervals of increase, decrease.
Oh, that's good.
Or here's another function, tell me the intervals of decrease. Like that, it's going to be broken into more pieces. Okay. Now, let's justify, since f prime at x is greater than 0 on the intervals -1 to 7/4 and 3 to infinity. So if the derivative's positive, what does that tell you about original function stated in words? If derivative's positive, f at x is
Increasing.
and okay, hopefully I've locked this into your brains when you write the intervals. Close them up except for infinity. So -1 to 7/4, 3 to infinity. since f prime at x is less than 0 on negative infinity to negative 1, 7/4 to 3, therefore f at x decreases on negative infinity to negative 1, 7/4 to 3. Yeah.
For like a rational function that is an asymptote, and you're trying to see increasing and decreasing, and you close it for that asymptote.
No, because there's no value there. You can only close it
So you
if there's a,
bracket?
yeah.
Okay.
You would keep it open at an asymptote because you can never equal, like the increasing doesn't start at the asymptote because there's no value, there's no point there. You only include it if there's a point. Okay. Now, before I go any further, there's one thing, we got so excited about doing increasing because we kind of forgot to do something. Once we found those three numbers, what should we do? Find the y values because those are going to be critical points in terms of graphing. So we're plugging -1, 7/4, and 3. Again, back into the original. So again, I don't need to see the, like, let me put -1 in everywhere there. Like, you could do that all on your calculator. At this point, grade 12, you don't have to show me that you can use function notation anymore. You can just do it. Just be careful, obviously. I think I shared with you guys the trick that most calculators will do if you store your number in answer. Then you can go like answer to the 4 minus 5 times answer cubed. So then you're not, especially with negatives, it keeps track of the negative a bit better than you do. Yeah. 222. Yeah. So -1 to the 4. So again, if we do that, -1, and you press equals, that usually stores your number into answer. So now if you go answer to the 4, okay, minus 5 times answer cubed, plus 2 times answer squared, plus 21 times answer, minus 18. So I got -31. So I have -1, -31. And then I put 7/4 in. This one's even uglier. Okay, 7/4. So 7, if you do 7 fraction button 4, store it as a fraction, then if you do everything, your result should be a fraction. Fractions are better if you can use them. So 7/4. Okay, if you use 1.75 though, it would be okay. Okay, I'm going to use the 7/4. So 7/4. So it's stored there, so it's going to be answer to the 4, okay, minus 5 times answer cubed, plus 2 times answer, sorry, oh, no 2 there, plus answer, did I do that? I hope I did that right. Did you guys get -31? Did anyone doing this with me? Okay, I'm going to double check that one, okay. I feel like I might have done a mistake. So answer cubed, 5 times answer cubed plus answer squared plus 21 times answer minus 18. So I'm getting ugly number.
This is not
-32. I was going to do this mentally. -1's not that bad. -1 to the 4 is 1. -1 cubed is -1. -1 times -5 is plus 5. I feel like I might have accidentally made that a 2. Minus 21. So 6 plus 1, 7. 7 minus 21. -14. -14, yeah. -32, my bad, guys. So -32. Okay. I'm gonna, I cleared it. I got a really ugly fraction here, okay? So that's where like having the convert button on your calculator is handy. I think I have 4.395. Yeah. So 4.3. Let's go with. I'm gonna be nice. I'm just gonna say 4.4. So there's your 1 decimal place. Okay, that on the test you actually can round to. So 7/4 is 1.75, 4.4, there's your y value. Okay, and then last but not least, I put 3 in. Okay, I'm just gonna do some mental math here. So 3 to the 4, 81. 3 cubed, 27. So minus 5 times 27, plus 3 squared, plus 9, plus 21 times 3, minus 18. I just got 0, I think.
Yeah,
Oh, because we already... Okay. So do you guys get too time consuming to find? It was, you could have factor theoremed it out, because there was a number that worked. Okay. Okay, anyway. Good. So I'm going to put a red box around that. So those are 3 critical points. Okay. So I did my increase and decreasing. So again, do you agree that then based on that and based on the sign chart, I now know what's really happening at -1 and 7/4 and 3? Local, we have a local min, a local max, a local min, but which of those would be the, like, it should make sense, guys. It's a quartic, okay? So do you guys get, it's a quartic with 3 horizontal tangents, so it's going to be like the W shape, yes? Based on those points, though, do we agree that there's 2 local mins at -1 and at 3, but one of those is an absolute min. The absolute min would be at -32. So again, just to save us time right now, I'm going to just say those are critical points. We're going to use our table to make our graph. In terms of understanding which one's local and absolute, it's all about comparing the y values and looking at the increasing, decreasing, what the sign changes are, right? So if it's positive to negative, it's a max. If it's negative to positive, it's a min. Good? Okay. So we now have everything to do with the first derivative found. But again, one extra piece that will help us is the second derivative to tell us the concavity. Okay, so concavity requires the second derivative. So the one good news is the second derivative will be quadratic. Yay! And then that's, you don't have to do factors here anymore. So derivative of 4x cubed, guys. 4x cubed is 12x squared. Derivative of -15x squared, -30x. And derivative of +2x, +2, derivative of 21. Okay, so there it is. Okay. So, I'm going to go through the process here. So let the second derivative be 0. We have 0 equals, is there anything factorable we can do here with this expression? Take out a 2, leaves you with 6x squared minus 15x plus 1. Is this screaming unfactorable?
Yeah.
What do I think?
No.
I'm feeling that the one at the end is making me a little scared, but it's probably not, okay? So, but because it's quadratic, it's not factorable, but is it solvable? Quadratic. X equals -b plus or minus square root of b squared minus 4ac all over 2a.
It's like the worst question.
The worst question? Well, if I do the worst question as an example, then it should only be uphill from here, right? Okay. 15. When I do quadratic formula, I like to show a substitution step, then I like to show a step where I go, where I just put whatever the number under the square root is. So I go, so 15 squared, 225 minus 24 is 201. Square root of 201 all over 12. So those are my exact answers for x. So then my approximate values are 15 I'm just going to do the minus one first, again, so that they're in order. So I'm going to go 15 minus root 201 equals divided by 12. So I'm getting negative 0. To round to the one decimal place, negative 0.1. 15 plus root 201 equals divided by 12, 2.4. Okay. And while I'm here, y values. Okay, back to original. This is the last time we're going back to the original. This is okay. So negative 0.1. Okay. So original. Negative 0.1. Negative. It would actually be better if you use the exact version, because then it'll be a little bit more accurate. So if I go 15 minus root 201 divided by 12. So now I have the 0.0685. Okay, so that's stored, and if I use that as my y value, answer to the 4 minus 5 times answer cubed plus answer squared plus 21 times answer minus 18, negative 16.6. Negative 16.6. And repeat with 15 plus root 201 equals divided by 12, 2.4, blah, 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 blah. So that's stored in answer. So now I'm going to go answer to the 4 minus 5 times answer cubed plus answer squared plus 21 times answer minus 18. So 2.1 approximately. So there are my last 2 points that'll help me anchor everything. So what do we know is going to happen? Well, we have to confirm it, but what's our expectation is happening at those 2 points? There are potential points of inflection at this point. To confirm they are, you're going to now check the concavities. This is the last little piece of the puzzle, and then we're going to sketch mode. So the last thing we're doing, so negative infinity to negative 0.1, negative 0.1 to 2.4, and 2.4 to infinity. Second derivative, original. So there's my sign chart for second derivative. Okay. So now I do this. So I'm picking basically any negative number will do for the sign check. So I'm checking, because it wasn't factoral, I have to do a little bit more work here, but again, it's not horrible. So if I pick a negative number, I can pick anything. Let's pick like negative 10 or negative, you really want negative, okay, negative 1, sure. I was going to try to be more extreme than that, but negative 1 is legit. So why don't we put negative 1 in here? Do you guys think I have to do a little bit more work because it wasn't factorable? So negative 1 squared is 1. 1 times 6 is 6. So I'm currently positive. 15 times negative because it was positive 15. So now I'm positive 21. Positive 21 plus 1 is positive 22. Times 2 is a
44.
So it's a positive. So my function is doing what? It's concave up. It's happy.
She's looking good.
Okay. And now, again, what's the perfect number to choose here? 0. Put 0 in. I'm all confused. So if I put 0 in, I get positive?
Yeah, you do. But do you?
She's a happy.
It's positive.
Mrs. One over there.
Okay, what happens for bigger than 2.4?
Maybe like 33.
Sure. 33. Why is it always positive?
They're all constant.
Did I copy a sign wrong?
I think it's positive 0.1.
Is it positive 0.1?
I might be wrong, but I think it was positive, unless we like change it.
That's disgusting.
Miss, the number is
I know.
12,080.
It is a positive.
It
Wait,
is a positive. No.
hang on.
What do we get?
There's no way you can draw this without changing the gravity. Agreed?
Oh, if you do the, no, you're right.
Okay.
Maybe accurate.
Yeah, maybe.
Okay. I'm not gonna.
Let's check. Okay, guys. This is a learning experience because this probably happens to you on a test. Oh no, things are not making sense. So let's go back. So I'm feeling pretty good about this. We got numbers that worked. Okay. So the derivative of 4x, so the derivative was 4x cubed minus 15x squared plus 2x plus 21. So then I took the derivative of that as 12x squared minus 30x plus 2. And I took out a 2. I took out a 2. I did that right. I took out a 2. 6x squared minus 15x plus 1. Negative b plus or minus square root of b squared minus 4ac all over 2a.
Yeah,
15. It's positive? Okay. So if that's positive, so that's the mistake, guys. 15 plus root 15 plus, so 15 minus root 201. Oh yeah, 5 by 12. So 0.01. Okay, so it should have been 0.1. So then is the negative 16.6 still good? I think
Yeah.
if I did this number, so this, I'm just gonna do a quick double check. So that number to the 4, answer to the 4, minus 5 times answer to the 3, plus answer squared, plus 21 times answer minus 18. I got error 1. Answer to the 4, minus 5 times answer cubed, plus answer, just 1 second, squared, plus 21 times answer, minus 18. I got negative 16.4. Is that what we got? Negative 16.6. I got this. So I think that part's okay. Yeah? It's 0.06, right? Yeah. Well, that's where I just rounded to the nearest decimal. There's 10. It's positive now. Yeah. So yeah, that was my mistake. And do you guys get that? Because and this is what, maybe I'll just highlight this. This is what makes it a little bit tricky about choosing a. So if that's positive, is that going to solve our problem? Because what was the number we checked for the middle? We checked 0, and that's zero is really in this one.
Oh.
So the middle, we could pick 0 for the first one and get our happy, right? But now I have to pick between 0.1 and 2.4.
We do 2.
Sure. And so if you pick 2 squares 4, 4 times 6, 24. 15 times 2 is 30. 24 minus 30 is negative 6 plus 1 is.
Frowny face.
So even though it's a frowny face, it's making a smile on the inside because that's what we expect to happen. You see what I mean? So that was our troubleshooting. You guys look at all the problems that it showed up because we messed up on a negative. Okay, so just be careful, right? And then this is positive. Okay. So there's my concavity. Okay, since f double prime at x is greater than 0 on negative infinity to 0.1 and 2.4 to infinity, therefore f is concave up on negative infinity to 0.1, 2.4 to infinity. Okay, since f double prime of x is less than 0 on 0.1 to 2.4, therefore f is concave F is concave down on 0.1 to 2.4. Okay. And therefore, the points we put in the box, after much weeping and gnashing of teeth, we figured this out, that they are points of inflection because concavity does change at those two locations. So, we have 2 points of inflection, 2 points of inflection, 3 critical points that are corresponding local mins and maxes, and we have the 1 y-intercept. There's other intercepts, we just didn't find them, so now let's try and start putting it all together. So when you look at the x, let's take a survey of all the x's we found. I see 0, 0.1, 2.4, -1, 1.75, 3, 0. Those are all of them. So I don't need to go very far from 0 to fit out all these points. Shall we go with like 4 ticks, like 1, 2, 3, 4 in each direction in the x? That will cover all of the values of x that are in my list, if I choose that. So that's what I'm going to do. So I'm going to put 1, 2, 3, 4. 1, 2, 3, 4. In terms of my vertical axis, I'm looking now at all the y values I need to worry about, and when I did my critical points, you see that one of them was -32, so I need to be able to at least fit -32. Everything else is closer to the y-axis, -16, so I need to at least be able to fit to 32. So shall we go 10, 20, 30, 40? Okay, so we'll go 10, 20, 30, 40, -10, -20, -30, -40. Again, if you want to just label -20, -40. Okay, so there's my axes with a scale. We're going to now plot the points. If you're plotting a point that's not on the axis, okay, can we just put like an indicator of, I'm going to save us a bit of stress about writing the coordinates, but you need to put like POI CP, just so I know what that point is supposed to match up with. Yeah. Yeah, just do a little calculation where f at 3 is. Yeah, that would be perfect. So let's start plotting. So 0, -18. So there's my y-intercept. 3, 0 is an x-intercept and a critical point. Okay, 7/4, that's 1.75, 4.4. So 1.75 is close to 2, 1.75, 4.4, so just under halfway up here. So this is a critical point. This is a critical point. That's a y-intercept. The other critical point's at -1, -32. So -1, -30 with a little bit underneath, so -32. So there's another critical point. Okay. And then, again, you could label all these with the coordinates as well. If it was a bigger grid, I probably would. I just want to get too crowded. And now there's also the points of inflection we found. So those occur at 0.1, -16.6. So 0.1, 16.6. Maybe I'll do them in red just to be different. So 0.1, 16.6. So essentially right there is a point of inflection, right? Okay, point of inflection. And at 2.4, 2.1. 2.4, 2.1. 2.4. So right around there is a point of inflection. Okay, so this part between these two critical points over here is going to be a bit annoying, but we can do it. We can do it. Okay. So here we go. Plotting time. Okay. So we agree that there's a couple more x-intercepts that are not plotted but have to be there for this shape to work, right? I have to go decreasing, increasing, decreasing, increasing. So again, remember I did this yesterday, guys. It's almost like lightly with your pencil, you just kind of go over top of where you think this is going to go. So it's going to be something like decreasing, increasing. Now, do you guys get that right here, very close to the y-intercept at this point right here, what does my graph need to start doing right basically at this red point? It needs to start changing concavity. So it's concave up, needs to be concave down from red to red. That's like color coding points of inflection might be helpful, because then you know I have to change concavity when I go into a different color zone. So I'm about to go into this red to red zone, so I have to be concave down. And then what has to happen from this red zone to the right has to be concave up, but what happens at this point, it needs to be a horizontal tangent. So do we see that's the shape we're looking for? Okay, so now I'm going to do it for reals. Okay, so one thing I am going to do is I'm going to go a little steeper than I did initially, because I think it makes more sense to go a little bit more like this. Curve. So I want to see the horizontal tangent there. I'm going to do it. I'm going to do it a little bit better. I'm going to go a little bit wider. I want to see a horizontal tangent happening there. So does everyone get that? I need to be concave up. Okay. Need to be concave up, go the horizontal tangent at critical point, and then I'm hitting this point of inflection. I got to be concave down until horizontal tangent there, concave down. Okay. Okay. And then to finish this off, so that's one. And then to finish off, I have to be concave up from after this red point, horizontal tangent, and then back up. So there's the function. I'll tell you right now, if you haven't done the back of the assignment yet, the back of the assignment's easier than this one. Yeah. Sure. Yeah. Yeah, go ahead. Okay? Okay.
Thanks, Liz.
Okay. So the idea is I want to see so notice that I didn't justify my min-maxes and my points of inflection. So I'll cut you a bit of a break on the assignment. If you've already done it, don't worry, okay? But as long as you justify the increasing, decreasing, those are the ones I really want to see as part of your solution. If the min-maxes and points of inflection just show up in the chart as correct, that's good. Essentially, just so you guys know, I'm looking at your chart as the main places where you're getting your marks. I'm looking at, I just didn't want those to come up with no evidence, so I'm looking at the rest as your evidence of how you're able to fill in the chart. So that's why you have to show your work. And then you're making your appropriate sketch. And then you do the one on the back. Everyone here got the assignment? Okay. So it's due tomorrow. There's about 10 minutes, 12 minutes left in this class, guys. If it's okay, I'm going to probably just grab a teacher to come in for like last 5 so I can go down and finish off the Euclid math contest with the students. But I'm here after school today if you have questions. Okay, and then tomorrow we're going to do word problem. The last topic is a little bit separate. It's a word problem, but you'll see how it's connected to what we've been doing. Question? Yeah. Okay.
No, you're